it says graph it as accurately as possible from 0 to 0.4. And so if we go ahead and just ask for what is e to the 0.1, we know e to the 0. What is e to the 0.1? So let's measure these as 0.2s. So we'll go 2, 4, 6, 8, 10. We'll call that 1. And then at 0.1, it's at 1.1. All right, 1.105. And then for e to the 0.2, it's 1.22. So at 0.2, it's just a wee tad above 0.22, so there it is. And then e to the 0.3, it's going to be 1.35. So 1.3 and another little bit, so it's going to be right about in there. And then one more, e to the 0.4 is going to be 1.5. So at 0.4, we're at 0.5. Okay, so there's 1.5, 1.2, 1.4, 1.3. You get the idea? And then this is 0.2 and 0.4 there, that spot. So that is e to the x in reality. Exact values, at least as exact as to 2 decimal places. So even that in and of itself is an approximation and is based on my ability to draw those. But that should be the exact solution, y equals e to the x. So now, the question said, based on your calculations in part A, how accurate is your estimate? Do you have a preference on, well, let's jump every 0.1 so that we can match this up with the dots that we just made. 19 on 9.2, Eulers method. So, our starting point is where?
1, 0, 1.
0, 1, right? So, that's the initial information. Our differential equation is y prime equals y. There it is. It took me a second to find it in the problem. Y prime equals y. There it is. Right?
And the change is change.
We're going to change by h's of 0.1. Agreed? Okay. So at the starting place, we need directions. We need to know where to go. Your test in a moment. So, what is the slope at this point? 0, 1.
0, 1.
Yes. It is definitely either 0 or 1.
Yeah.
Which one is it?
1. 0. 0. 1. It's 0.
You're so solid in our opinion on this.
I hate when teachers do that.
No, this is why they do it.
You say the right thing and then they act like you're wrong and then...
There's a whole education class on it.
Is there?
No.
That is called sarcasm.
Lesson number 532. This is an x and a y, right?
Yeah.
We know this from 5th grade. Yeah. And we know that the slope, in order to satisfy the equation, must equal y.
Yep.
Our y is 1. Therefore, the slope at 0, 1 is
1.
1. Okay. That's good. It's good that we know this. So, y prime evaluated at 0, 1 equals 1.
It's so much better right now.
Okay? Does that make sense?
Yep.
Okay. So now you need an equation. in order to tell you exactly how to do this, like having GPS, right? It actually maps the line out for you that you're supposed to follow, right? And so you have your point slope form, y minus 1 equals the slope times x minus 0. That's the curve we're going to follow. We're going to follow it from x equals 0 to x equals 0 plus our h, 0 plus 0.1. So new x is, now x is going to be 0.1, right? And so y will equal 1 times 0.1 plus 1, or
2.1.
right? Okay, 1.1. So now at 0.1, 1.1. Okay, we've moved over 0.1, which is a fixed distance, and we've moved up a calculated distance of 0.1 to 1.1. The fact that they're the same is a coincidence, or I don't know that you can really use the word coincidence in mathematics, but it certainly doesn't have to match. It does in this particular problem. So going over here, we started, and then here we are pretty much right on track to the level of accuracy that I can actually plot on there. I pretty much plotted that at 1.1, and that came out with an estimate of 1.1, so it's pretty good. If I recorded in a table my calculations, which I actually could have since they're still here on the calculator, this was actually, let's see how I want to do this, at 0.1, I got 1.105, and at 0.2, I got 1.221, and at 0.3, 1.350 if you round, at 4, one more, there it is, 1.492. Okay, this is exact. This is your x, this is e to the x. Okay? Here's Eulers' method, and it came up with 1.1. Darn close, but not perfect, right? But as far as our plot is concerned, it's going to be hard to graph thousands, even 5 of them. It's going to be challenging. All right, once you're there, then you can continue. Now you have this new location. You ask for directions. What direction should you go in? What's your slope?
1.1.
It just picks off the y coordinate. Y coordinate is 1.1, so there it is. And now we need to follow the line. This is our yellow brick road. 1.1, 1.1, x minus 0.1. Now x is no longer 0.1, now x is 0.2. So y equals 1.1, 0.2 minus 0.1 plus 1.1. If you look in the book, again, reminding you, and for those who were absent, the 0.2 minus 0.1 is always going to end up being your h right here, and so the book doesn't even bother writing the 2 out, even though it comes from point slope form, and you're following the equation of a straight line, and in my opinion, that is the easiest way to understand why and where all this comes from. If you look at the book, they're just going to put an h or a delta x there, and it becomes a little mysterious, but that's where it comes from, in my opinion. I thought when I read it once upon a time, eons ago. What's that?
I hate the book.
Well, everybody always, I've never found a book that at times I or my students or both haven't hated. It's a pretty well-known fact that there is no perfect book for everybody. This book is only perfect for one person in all of the world, Stuart. Stuart thinks this is a perfect book. This is exactly how, and actually that might not even be true. He may have felt tied the same way I would if I wrote a book, that once you write it down on paper, mathematics is such that you have to be so precise. You can't like wave your hands at anything or really fudge anything to make it more clear if at the same time it makes it so that the math isn't perfectly valid to any level of scrutiny. Because mathematics is like that. It's kind of perfect. And
I don't like mathematics.
so
Math
in a lecture, Q&A, discussion, it's kind of like this, or imagine that sort of sense. You have a degree of freedom that the printed word does not allow, because that is a permanent record. For instance, if this were being recorded, I would have to be really careful that I don't say anything that could be misconstrued or was mathematically iffy, because then it could come back to bite me. It's bad. Right, Roger? Okay, so there you go. This is going to be your point 1. It's your h. It's always your h. There it is. 1.1 times 0.1. What? That's what you do when you're trying to catch. What was the question again? That's how you vamp for time, right?
0.11.
1.21.
Maybe.
Maybe.
Okay, so.
Maybe. Yeah.
This is really sad.
This is calculus, not arithmetic.
Exactly. It's like, I'm a calculus student.
0.012. No, 0.121.
1.21.
Wait.
You get
0.121.
1.1 times
1.12.
0.1 is 1. You move the decimal over one place. Never mind.
0.0121.
Point 1 is division by
1?
2 places.
10,
Yeah.
right? 1/10.
Yes.
Division by 10, you move decimal place 1. It's
Yeah.
1/1.
0.11?
Point 1.
Yeah, 0.11.
Division by 10. You just move the decimal place.
Oh, drats.
Drats.
That always gets everybody. Wait, there's 11s. It's got to be have a 2 in it.
No, it doesn't.
If it wasn't for that meddling decimal point.
And now you can say, oh, that's what I meant. I was talking about the final answer. All right, so 1.21 is where we're at now. So over here, not 1.22, but 1.21 is what Eulers' method gives. Again, you're going to be hard pressed to tell the difference on my little plot here between the blue and the yellow dot. Okay? Because we already talked about with the computer model that a step size of 0.1 is pretty good. It's a decent step size as far as accuracy is concerned. All right. Does this satisfy your curiosity? Do we need to keep going?
No,
Just 2 more times
I was just messing
in
up
order
over
to
in the
satisfy
x,
problem?
the x part. So the next one would be x would equal 0.3.
Yes.
All right, that's all I need to know.
Okay. So your next step would begin with you now being at 0.2 and 1.21. Your slope would be 1.21. Your new x would be 0.3. And you would start the process over for the 3rd time.
Oh my god, that's horrendous.
Yeah, this method is much easier than the book's
The
version.
method didn't come into heavy usage until the advent and development of computer technology. It's called Eulers' method, which dates it back a few years, and 1 or 2 before the advent of computers. So it's a valid technique for approximating differential equations, but it wasn't an effective way until computers cut the time that it takes to do this down to that,
The iterations.
right? Because it is, it's just an iterative method, and it just repeats the same thing. It's what computers are great at, repeating the same stupid thing over and over and over and
Yep.
over again. Right, so that's what they do.
Live
Right.
life.